8.7 Solving problems with exponential and logarithmic functions. When we have a range of values that vary greatly, we can use a logarithmic scale with powers of 10, and it helps us make comparisons between large and small values. We apply logarithmic scales in calculating pH, the Richter scale that calculates intensity or magnitude of earthquakes, the decibel scale, which is used to measure the loudness of sound. So we're going to look at applications involving these kinds of scenarios. First example, the intensity of one sound can be compared to that of another sound of the same frequency by taking the ratio of their exponents. L equals 10 times log of I divided by IO, where IO is the minimum intensity detectable by the human ear, and I is the intensity of the sound being measured, and L is the loudness measured in decibels. Question is, a busy street has a loudness of 70 decibels. How many times more intense is the street noise compared to the minimum decibel detectable level? Okay, so we're going to use the formula we have been given, which is the loudness of sound L equals 10 times log of I divided by IO. So in this busy street, the loudness is 70 decibels. And they're asking how many more times intense is the street noise compared to the minimum detectable level. The minimum detectable level is IO, which is given to us here. And we're going to say that 70 is equal to 10 times log of I divided by IO. And we can divide both sides by 10. We get 7 equals log of I divided by IO. We take the exponent, take them both to exponent 7. So 10 to the power of 7 is equal to 10 to the power of log to the base 10 of I divided by IO. So 10 to the power of 7, this simplifies to I divided by IO, because we know this relationship, right? And therefore, the ratio of those intensities is 10 to the power of 7. So therefore, since I divided by IO is 10 to the power of 7, or is 1 with 7 zeros. So that many more times louder is the street sound compared to the minimum detectable sound. So therefore, the street is 10 to the power of 7 times more louder than the minimum intensity detectable by the human ear. A normal conversation has a loudness of 60 decibels. How many times more intense than a normal conversation is shouting, which has a loudness of 80 decibels? So let's compare the two of them. One is, let's compare the normal conversation and compare that to shouting. So in a normal conversation, you have 60 decibels of sound is 10 times log of I divided by IO. And for shouting, which has a loudness of 80 decibels, is equal to 10 times log of I divided by IO. Here you divide both sides by 10 and you get 6 is equal to log of I divided by IO. And just like we did in the previous question, 10 to the power of 6 equals I divided by IO. And on the right side, you divide both sides by 10. 8 equals log of I divided by IO. 10 to the power of 8 is I divided by IO. So you can see that if you're comparing the intensities, let's call this the intensity of a normal conversation. Normal conversation, and this is, you know, the intensity when you're shouting. So if you divide IS divided by IO with IN divided by IO, this will be, or we could, you know what, to make it even easier to compute, let's just say that this would mean IN equals IO times 10 to the power of 6. And over here, IS can be written as IO times 10 to the power of 8. So if we compare IS and IN, their ratios, IS is IO times 10 to the power of 8, and IN is IO times 10 to the power of 6. So it's 10 to the power of 8 minus 6, which is 100. So that means that if you're shouting, it's 100 times more louder than normal conversation. Okay, so therefore shouting is 100 times more intense than a normal conversation. So we can compare intensities when we do these kinds of comparisons, rather than if we just look at 60 and 80, we can't really tell how many times of a difference is going from 60 decibels to 80 decibels. But when we actually compare them like this, we can say that it's 100 times more intense than a normal conversation if you're shouting. Okay, here is the earthquake problem. The Richter scale was introduced by American seismologist Charles Richter in 1935 to measure the magnitude of earthquakes. The magnitude of an earthquake of intensity I measured on the Richter scale is given by the following equation, where IO is the minimum measure of a reference earthquake. An earthquake with a measure of X on the Richter scale has a true intensity of 10 to the power of X. So here's the formula. The Richter scale value of the magnitude of an earthquake is equal to log of I divided by IO. So question's asking, if the earthquake has an intensity of 10 to the power of 7.8, what is the magnitude on the Richter scale? So an earthquake with a magnitude of X on the Richter scale has a true intensity of 10 to the power of X. So therefore, the true intensity is 7.8. Okay. Sorry, the magnitude is 7.8, not the true intensity. Intensity is 10 to the power of 7.8. Therefore, the magnitude of the earthquake is 7.8 on the Richter scale. How many times more intense was an earthquake that measured 8.3 on the Richter scale than an earthquake that measured 5.7? So you have two comparisons to be made. One is an R value of 8.3 and the other one is an R value of 5.7. So how much is the difference? So for this one, we have the the formula, R is equal to, so log I divided by IO. So 8.3 is equal to log of I divided by IO here, and here 5.7 equals log of I divided by IO. And 10 to the power of 8.3 equals I divided by IO here, and 10 to the power of 5.7 equals I divided by IO here. And I'm going to call this I1 and I2 just to differentiate between the two intensities. So in this case, I1 is IO times 10 to the power of 8.3. In this case, I2, the intensity of this earthquake, is IO times 10 to the power of 5.7. So if I compare the two intensities, the ratio of their intensities, it would be IO times 10 to the power of 8.3 divided by IO times 10 to the power of 5.7. So it's 10 to the power of 8.3 minus 5.7. And that works out to approximately 398 as your answer. So therefore, the earthquake with a magnitude of 8.3 is 398 times more intense than that with a magnitude of 5.7. Okay, so that's our answer. In chemistry, the pH of a solution is a measure of its acidity. pH value is defined by pH's negative logarithm to the base 10 of the hydrogen ion concentration, where hydrogen ion concentration is in moles per liter. Find the pH for tomatoes if the hydrogen ion concentration is 6.3 times 10 to the power of negative 5 moles per liter. So pH is negative logarithm to the base 10 of hydrogen ion concentration. For tomatoes, the concentration is given as 6.3 times 10 to the power of negative 5. So it's minus of log 6.3 times 10 to the power of minus 5. And using the law of logarithms, we can say this is the same as log to the base 10 of 6.3 plus log to the base 10 of 10 to the power of minus 5. And this is log of 6.3. We can bring the negative 5 down here, so it becomes minus 5 times log 10. We can distribute the negative into the brackets. We get negative log 6.3 plus 5 log 10. At this point, we can enter it into our calculators. We get negative 0.8 plus 5, which is 4.2. So that is the pH. This is the pH value of tomatoes. And pH, you can have something that has neutral pH, as it has lower values. Neutral pH is 7. Anything less than 7 is acidic, and if it's greater than 7, it's alkaline. So this value is 4.2, so therefore the pH of tomatoes is 4.2. So you can see that it's acidic, okay, because it's less than 7. Now, the pH of seawater is 8.5. Find the hydrogen ion concentration. So the definition of pH, it's negative log to the base 10 of the hydrogen ion concentration. In this case, seawater has a pH of 8.5. It's a negative log of hydrogen ion concentration. So let's take both sides to the power of 10. 10 to the power of 8.5 equals 10 to the power of, you know what, before we do that, let's get rid of the negative on the right side by dividing both sides by negative 1. So we get negative 8.5 equals log of the hydrogen ion concentration. And then take 10 to the power of each on each side. 10 to the power of negative 8.5 equals 10 to the power of log to the base 10 of hydrogen ion concentration. So that is negative 8.5 equals hydrogen ion concentration, and 10 to the power of negative 8.5. You take that in your calculator and you would find that the hydrogen ion concentration equals, and you calculate, this works out to 0.000000003. Or you can say that in standard form, you'd write that as 3 times 10 to the power of negative 9, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so that much is the concentration of hydrogen ions in seawater. In chemistry, we have this definition of pH. How much stronger is an acid with a pH of 1.9 than an acid with a pH of 3.8? So we'll compare two different types of acids. One has a pH of 1.9 with another which has a pH of 3.8. This is, of course, more acidic, but how much more is it compared to these? What do these numbers mean? So this one's pH, negative log to the base 10 of hydrogen ion concentration. 1.9 equals negative log of a hydrogen ion concentration. Here, 3.8 is negative log of the hydrogen ion concentration. So 10, and then we divide both sides by negative 1. Same thing here, by negative 1, and we get negative 1.9 equals log of the hydrogen ion concentration. Negative 3.8 equals log of the hydrogen ion concentration. And to find this, 10 to the power of negative 1.9 will work out to the hydrogen ion concentration here, and 10 to the power of negative 3.8 will be the hydrogen ion concentration here. So this works out to, on your calculator, if you take, let's call this solution 1 and solution 2, if we compare the two solutions, so we take the hydrogen ion concentration of solution 1 and divide it by the hydrogen ion concentration of solution 2. So it'll be 10 to the power of negative 1.9 divided by 10 to the power of negative 3.8. Put that in your calculator, and it works out to approximately 79.43. So therefore, the solution with a pH of 1.9 is approximately 79 times more acidic than the solution with a pH of 3.8. Okay. You can now practice questions.